Good evening to everyone gathered here. Thank you to each and every one of you for being here with us at this 5-day International Virtual Faculty Development Program. The beginning is the most important part of success. With this note, I express my hearty welcome to our chief guest, Dr. Pratibha Verma, Assistant Professor, Faculty of Engineering Technology, Siksha O Anusandan, Bhubaneswar. For this beautiful occasion, welcome you, ma'am. It is my pleasure to welcome Dr. N. Muthmani ma'am, Principal, PPG College of Arts and Science, for this wonderful knowledge sharing session. Welcome you, ma'am. I am very happy
Thank you
to
so much.
our head of the department, Mr. V. Ratna Kumar, Assistant Professor, Department of Mathematics. Welcome you, sir. I express my sincere welcome to the participants from various colleges and universities. Welcome you all. On behalf of our department and my own behalf, once again, I welcome you all.
Thank you, ma'am. Take time to gather up the past so that you will be able to draw from your experience and invest them in the future. I request Mr. V. Ratanakumar, Assistant Professor and Head, to introduce our chief guest of today.
A happy and pleasant evening to all gathered here. I'm very glad to introduce our resource person, Dr. Pratibha Verma, Assistant Professor, Faculty of Engineering Technology, Siksha O Anusandan, Bhubaneswar. Ma'am has completed her undergraduate studies at Mahatma Gandhi Kashi Vidyapith in Varanasi, Uttar Pradesh, and her master's degree from Motilal Nehru National Institute of Technology in Allahabad. Additionally, Ma'am obtained her Doctor of Philosophy from Motilal Nehru National Institute of Technology in Allahabad. Her research interests include fractional differential equations, numerical analysis, as well as the theory of existence and uniqueness in differential equations. Ma'am holds 5 years of teaching experience in engineering mathematics at the Institute of Technical Education and Research, Siksha O Anusandan, Deemed University in Bhubaneswar. Ma'am has served as a reviewer for a significant number of international journals and qualified the IIT JAM exam in 2014 and cleared the GATE in 2018. Ma'am holds a diploma in computer application and has completed numerous online certificate courses. Ma'am has actively participated in a vast number of conferences, workshops, and seminars. Ma'am has published 2 book chapters, 15 research papers in international journals, and has 5 research papers currently under review. With this concise profile, I'm delighted to extend a warm welcome to you for this session, ma'am.
Working with great people makes you great. You learn a lot, and it also gives you the experience and confidence to move on with your own career. May I request Dr. Pratibha Verma, Assistant Professor, Faculty of Engineering Technology, Siksha O Anusandan, Deemed to University, Bhubaneswar, to take over the session.
Okay. Thank you very much for your introduction and your welcoming nature. And I Pratibha Verma, and today I'm giving a talk on fractional differential equation and application. And first of all, I would like to thank Dr. Kumar for inviting me this lecture. So in this talk, I would like to discuss about the different kind of solutions and for fractional differential equations, and also a part of analysis in which I have established the existence uniqueness condition. Of course, these all are my research area. So I would like to discuss this all some fractional differential equation and applications and the analysis parts. So in this title, I have included the solution analysis, and this arbitrary means I have discussed the several kind of order. So differential equation we all are familiar. So the order of a differential equation we know as a integer. but there are also some extended version already exist in our literature and research, and some author very well contributed in this area. So basically, I'm going to discuss the fractional differential equations and the variable orders and the complex order. This all are the order of the differential equation. So in this particular talk, I have described all these three type of differential equation with different kind of orders. So these are the outline of my presentation. In the introduction part, I have covered the introduction of fractional differential equation, applications and methodology, and the discussion of the methods and the derivatives of the fractional operators. So, and in the further, I have described the fractional differential equation. How can we describe the fractional differential equation and the application of the fractional differential equations? And these are the three method: add-domain decomposition method, and these are the two modify and two-step ADM. Basically, the modified version of the add-domain decomposition method. And also, I have included some example based on these three method. I have solved via these three method, and also we will extend our this example for the different kind of differential equation. I will also give the idea how can we extend the research in this particular fractional problems. And also I have used two types of fractional fixed point theorems, and you can use also different kind of fixed point theorems, but I have used two particular fixed point theorems, Shepherd and Klafnol-Key, but there are so many theorems also exist you can also use. And this basically our main target to reduce the assumptions and the conditions and so many things, so that we are easily applicable and easily implement on the problem, and we obtain the effective result. And one example I have discussed in this talk for the using the for establish the existence uniqueness condition and the inequality I have established. And the final conclusion based on our talk I have described in the conclusion part. And also I am giving some idea about the future work in the future work section, and we will see part wise. Now this is the introduction for the fractional calculus. So fractional calculus is the developed or developing both, because the some are the developed and some are the developing because of the advantages. This is very famous topic, and we see, and this is also very frequently used in the differential equation because of this property and advantages. So basically the this actually application is very vast, and the engineering science they all are using the fractional calculus, fractional derivatives. Whenever, whereas if we are using derivatives, it means we can able to use the fractional derivative, and we are able to use the fractional calculus. So this is the main idea. So now why we use the fractional calculus and of course fractional derivatives? Because of the advantage, because of the accuracy of the solution. Of course, we if we have the fractional, if we have differential equation, so our target to find the solution. If a solution is obtained, then we are able to obtain able to observe the nature of the problem, because every differential equation based on the real world problem. So if we are able to find and we are able to see the close and accurate result, so then we can judge the basically the future results. So now one by one we will discuss. So but also there are some disadvantage of fractional derivatives, because the non-local property yet it is not well described in the literature. Also geometrical interpretation is also not actually discovered, and also we are not able to visualize properly as compared to the standard derivatives. So these two actually area is also these two area actually developing, because some author giving the concept based on their assumption, but at this is the not exact meaning of the geometrical interpretation, and the of course local non-local criteria of course must be described. So due to some lack of property, the derivative is not actually give the exact and refined visualization of the derivatives via using the fractional operators. So these are some application in which I have given some point of application, like memory effect, image processing, and the porous media economics. There are so many application of fractional calculus because we have already bunch of research article we have based on the applications and the solutions, so we can easily obtain and we can easily read the application of such kind of research. So in the memory effect is very fractional derivative is very useful because of the, if we try to find out, if we try to restore the memories, so ordinary differential equation is not applicable, but via fractional derivative we are easily to restore the memory if we lost the memory in the previous data. So this kind of application is also used in the fractional differential equation. And now the image processing, via this two image we are easily to observe the effect of fractional derivative. So A and C are two images given in this slide, where A is the blur image, original image, and now we are trying to improvise this image via the our fractional derivative. So if we are trying to model this image, and if we model and then apply the fractional derivative, so via the via the implement of the fractional derivative, we obtain this image B at alpha, where alpha is the fractional order, and at 0.53 this image will be better than the original image. Similarly, in the same case, C picture is also blur and destroy image, so we can modify, uh, we can accurate this image via the fractional derivatives. So CD is also improved version of this original image. So these two images clearly see, we can see clearly observe that fractional derivative is very useful for such kind of process, image process. So there are so many article also describe in this discuss in this kind of work. So particularly for reference 4, I have read, and via this, and this image also taken from this reference. So now porous media economics, there are so many application actually discussed. So these are the application of fractional differential equation. So but our main target, if we develop, if we are working on real world problem. So if we are working on real problems, so we actually if we use the modeling, and after modeling we obtain the system of differential equations. So now the differential equation is the order, where the order integer, then we are converting this order into the fractional because of the solution. So with the help of fractional derivative, we are able to find the tendency, how it's the cover the range. So basically, so our target to find out the solution of fractional differential equation. So there are so many numerical method actually developed. There are a few of them actually listed in this slide, and in which the first one I have focused in this talk, and these are all second to up to 10. This is also very useful method, and also actually in the different several research paper you can see. So in the particular problem, the particular method will be more effective, and some are not effective, because these are the numerical method, there are advantages and disadvantages. So I can't say this method is best, this method is worst. So this is not case. Some type of problem may be where variation iteration method may be more effective than domain, and so in some kind of problem domain is more effective than others. So these are the based on the problem to problem, we can check and compare, and we see the result, and which one is the more effective, we can comment on that. So now I'm going to describe the method. Before that, I want to discuss the domain method, introduction of domain decomposition method. So basically, domain decomposition method is based on is applicable on the nonlinear differential equation. In general, this method provides the exact solution for linear differential equation, but our main target, because every real problem basically provides the nonlinear differential kind of differential equation. So the domain basically more useful for non-linear type of differential equation. So because in general, if you are trying to get the solution for the non-linear differential equation, first we convert each non-linear term into the linear term. This is very hard to process and very complicated. So via domain decomposition method, we directly implement this method on the problem without converting the method, without using the perturbation parameters in the homotopy perturbation method. This kind of, because this type of thing actually this type of thing actually recreate the problem. And if we are just creating the problem, so it means the error will be occurs. So it means the domain actually provide the direct implication on the problem without converting the non-linear term into the linear and others using the other tools. But here we are using the some special kind of polynomial, so we will see in the description of the method. Also the domain provide the series solutions. This is also advantage or disadvantages. So of course we have, I already say every method had disadvantage and advantages. So while removing the one by one, we are trying to modify the method. So in the domain process, there are so many modification also happen, and some are method modify version of domain decomposition method very well uh, well uh, well implemented, and well result actually provided in the research papers. So I will actually discuss one by one. So convergence rate is also very good in this method, and this method provides the semi-analytical solution. In which this method is not a numerical, not provide the numerical solution, it provides the semi-analytical solution. So now the of course the modification I've taught about this. This means there are so many modification actually discussed in the research paper for removing the disadvantage of domain decomposition method. If some problem actually in domain decomposition method on some problem is not well performed, so we are trying to remove the disadvantage of domain decomposition method by using the small change. So modify domain decomposition method, new improved domain decomposition method, improved and two step. There are so many actually improvised version exist in the literature we can actually see. So but only few version actually frequently used and some are not, but they are also very good for form in on different kind of differential equations. So we can discuss one by one the problem. If problems coming, then I will discuss the method. So, but in my opinion, if the two-step domain decomposition is best if it is applicable on the problem. Applicability means I will discuss by example. So, if TSDM is applicable, then it's provide the exact solution. In general, the fractional differential equation does not exist the exact solution if in the homogeneous case. But if our fractional differential is non-homogeneous, then we are able to find the exact solution via the SADM. So this is the advantage of TSADM. So in general, exact solution is very hard to obtain. So we are applying the different kind of different numerical method for getting the approximate solution. But TSADM, in the TSADM case, we obtain the exact solution in just few iterations. So this is the advantage of the TSADM, and which is the actually modification of ADM. So now the domain decomposition method is useful. So because it's old, but if there is so many version exist, and if we are able to apply, then it will provide the more better result than other existing numerical method. So now next, this is the actually the this is like based on the fractional operators. uh, this operator basically before solving any kind of fractional differential equation, we first choose which definition we are going to follow. So these are the some classical fractional derivatives are listed in this slide, in which the fourth one, capito, is the very important because of the property of this capito derivative. These all are the classical because they are very old derivatives. The new derivative actually discussed in this era. This is the some fractional operator listed in this slide, which is very this is the new operator, because this is the classical which is used in the previous past, but in this case first, second, third are not so much used in our problem solving. So hardmark, capito, and the research and tempered, these four are very useful and uses by the different kind of researchers. So in which the main I have used capito derivative for solving fractional differential equation. Hardmark is also very well performed, but capito provide the main advantages, main property, same as the standard derivative. I will discuss in the further slides. And this is the new operator in with the Hilfer, capito Fravagio, Ategana, and the Prabhagar is also very well performed, in which this 6 and 7, the application of this fractional derivatives is more used in the signature verification and etc. So this two derivative is very famous now, and this derivative based on the singular non-singular kernel, whereas the capito is based on the singular kernel. So because of non-singularity, the application of this derivative is in the different area is more useful. So now our focus our main choice, our main focus of the fractional derivative on capito fractional derivatives. So why we choose this fractional operator capito? Because of the main property is this main property is the given in equation 7. So we see the derivative where d is the capito derivative, fractional derivative, where the sigma is the fractional order. So if we apply the capito derivative on constants, provide the 0, same as the standard derivative. So in general, the other derivative which actually discussed in the previous slide, classical and new, so these are not provided this main property. So due to this property, we are able to find out the exact solution, and this is the very advantage of this capito derivative. So now see, this is the one, and this is the main definition of this derivative, and after modifying this the definition, we obtain the capito. So that's why we have described this definition first, then modify this derivative and obtain the capito. So basically this z sigma y, actually the integral operator, where the sigma is the fractional order. So this means this operator means the fractional integral with order, so fractional order sigma with respect to y. So if we choose the 0, so sigma is equal to 0, then we obtain the same function after applying this z operator. And this is a property, and via this property we see that applying this to z, this is the add-on, and then obtain the value of the integral of gy. And this is the commutative property hold by the property 3. And the z and d operator, via z and d operator, if we are trying to obtain the value of polynomial for fractional integral, this is the direct formula obtained from this equation 1. And the derivative, if you are trying to find out the fractional derivative of a polynomial, so this is the formula. Directly we are putting the values of, we will obtain these values. And also for the special case trigonometry exponential, so we already just use this definition and obtain the formulas. So also we have direct formula given in the research papers. So this is the capito mean, this is the definition. Equation 6 is the capito fractional derivative, in which see this is the g to power and xi, where the if we if gy the constant becomes 0, so given in question 7. So this is the main property and main advantage of capito, and that's why I am using this, because I am our main target to find out the exact solution of the fractional differential equation. So this property is property 7 is very useful for us. And now the linearity property also hold by this capito derivative, and is the second version of capital derivative definition, and we see the if we apply the fractional derivative on fractional integral and fractional integral on fractional derivative, both give the different quantities, and this both are not equal to both are not equal. So it means the commutative property actually not hold via these two operator. Now, these are the two propositions are very useful for finding the solution of equations 12 and 12, 13, and 14. Now, this is the picture where the d is the derivative and beta is the fractional order of derivative, where beta may be belong in the integer or non-integer, and beta may be variable, and the beta may be the complex number. So, but in this case, in our lecture, we will discuss all three of them, where the beta may be non-integer, beta may be variable, or either beta be complex number. So, in this slide, I have described the one problem for fractional differential equation, where d alpha basically the fractional derivative, and I have choose Caputo derivative for solving differential equations. So this the proper name is d alpha is the Caputo fractional derivative with alpha order, and where this gy basically the source term or force term, and this whole equation is the non-homogeneous equation, and this z in the capital H basically this is the general problem in which the capital H function of this four terms, where the alpha 1 alpha 2 are the two different fractional derivative, capital fractional derivative. So this is the multi fractional order differential equation, because in this equation three fractional derivative involved with the initial condition. This is given in equation 16. So now our target to find out the unknown value of xi, and of course this unknown value of xi is the solution of equation 15, whereas the alpha 1 alpha 2 belonging the two consecutive number n minus 1 to n. So always fractional order always belong in the two consecutive number either 0 to 1, 1 to 2. So these are the actually specify numbers for the particular problem. So now, now I'm going to describe one by one the method. Three method I have discussed: adornment decomposition method, and two-step adornment decomposition method, and modify. These three are our main target for this particular talk. So now the equation, first we actually rewrite this equation 15 as a operator form. So basically this is an operator form in which this is the fractional derivative term, and Lj basically the linear term involved in the original equation, and Nj basically non-linear term involved in the given equation, and Gy again source term or linear force term, and alpha is the again belonging the two consecutive number according depend on our problem. So now this dy the fractional derivative, now applying the z operator in both sides, we obtain our unknown solution in this form. So this is the formula, actually proposition 1 and 2 used in this equation 18, and we obtain this expression given in equation 18. So according to a domain decomposition method, the xi, of course, the solution in form of series. So this is the solution, unknown solution given in equation 19 in the form of the series, where xi and basically run from 0 to infinity. We terminate over the series and obtain the solution. So the termination point is the important, and of course series must be convergent. So this is the condition for the obtaining the semi solution for the using the adornment decomposition method. So now our main complicated point is how to tackle the nonlinear term involved in the differential equation. So basically, if now basically in this case we actually approximate the nonlinear term into the value, approximate the into the by using the special polynomial called as the adjoint polynomial. So this Bn is the called as the adjoint polynomial. So one by one we obtain the value of adjoint polynomial and we approximate the linear term via this adjoint polynomial. So with the help of this series, the equation 1 represent the main recursion formula. So with the help of this 22 equation, we obtain this first iteration J naught, and the further iteration based on J naught, we obtain the J1, J2, and J3. And this eta capital N basically provide the derivation series. And after applying this limit form provide the our exact approximate solution. So basically, this is our desired solution based on the Adorman decomposition method. So of course, this series must be convergent. If not, then here the Adorman decomposition method is failed, and then we are not able to find out the exact approximate solution by using Adorman decomposition method. So, but there is also some modifications so that the series must be convergent. So there we have some criteria so that we can able to check series convergent or not, and this method is applicable or not. There are if we study the method one by one, we can easily see which method is more applicable on the problem. So now the second method is modify adjoint decomposition method, in which we in the previous slide we obtain the J naught with the help of adjoint decomposition method equation given in equation 23. So this J naught can be splitted. Suppose there is an assumption in modify adjoint decomposition method. Suppose J naught is split into two components D1 and D2. So the modify recursion formula, modify recursion values, basically J naught is the first term of this splitted form D1, and the second will be the D2 minus the first term this other term based on the J naught. So basically these are the modified recursion formula. There is the only slightly change values, and due to this the computation effort will be less, and the convergence more faster than the adjoint decomposition method, because in the some cases J naught is more complicated, means the first term is very complicated and the tackling this term is very hard to manage in the further iterations. So here, via splitting this term, we reduce the computation, and if we are reducing the computation, of course the convergence rate is more than the adjoint decomposition method. This accelerate the convergency rate via this modify adjoint decomposition method. But again, this method is based on the assumptions the first or initial term must be split into the two component. If not, then again this method is failed. So but if this method is applicable, then this method is very good for solving the numerical for obtaining the numerical solutions. So now next method is two-step adjoint decomposition method, and of course, with the via this name, we clearly means two-step. The method involves two step. In one step, we obtain the exact solution. If the first step is failed, then we go to the second step, and second step provide the numerical solution. So our main target to solve the consider problem in the first step. If first step is capable to solve the problem, then is provide the exact solution, and it will very the a good commitment by this method. So now the again this method is based on the assumption, so that the this J naught again is split into the several component. If the J naught is split into several component, then we one by one choosing the component and try to satisfy the component chosen component by the original problem or the associated condition, like initial condition or boundary. If the suppose we are choosing the J naught, if J naught satisfy our equation or the associated initial or boundary condition, this means the J naught is the exact solution of our equation. If not, then we go to the next component, and then again we are trying to verify the component. If then verify, then this method is the first step is successful if we are capable we are able to find out the term which actually satisfy the equation and the conditions. So this if there is no term actually involved in the giant knot, so that is actually very satisfy the equation or associated condition, then the first step is failed, and then we go to the next step. In the next step, we are apply the adamant decomposition method and find out the approximate solution. In the first step, we obtain the exact solution by the assumption, where the assumption xi naught must be split into several component. In if not, there is no there does not exist a term which actually satisfies the condition or associate condition, then the first step is failed. Then we go to the next step, in which we applying the adamant decomposition method and obtain the approximate solution. So here maybe we have an idea. So in the paper, in the literature, the second step we applying the adamant, but here we have a choice. In the second step, we can use any other method composition of methods, and of course adamant, in which we are applying the adamant polynomial. So without using the adamant polynomial, we can obtain the solution with the help of a different polynomial if we use in place of adamant polynomial. So this is the idea. We can improvise the method with the help of a different polynomial using in place of the adamant polynomial. So we can actually some of research article actually discuss this type of problem. So now the advantage and disadvantages. Of course, advantage of TSADM is provide the exact solution in just one iteration, because Jai not actually provide the exact solution. If within the Jai not there exists a term which actually satisfy the condition and associate condition. If not, so it means it's not provide first. So disadvantage, it means the Jai not may be not split into the several component, and if the source term or boundary condition or initial condition are zero, if it means the fractional differential equation are homogeneous, or associated condition and the modify and boundary condition are not contributed. So basically the TSADM is failed, and then we are not able to find out the exact solution of the considered problem with the help of this method, because the J not become zero if our initial or boundary condition and the source term will be zero. So J not will be zero. So this is the trivial condition. In this case, the TSADM is totally fail, and then we are not able to get the solution. But in complicated case where the source term is non-zero, so it very helpful to find out the exact solution. We can see in this further slides. So this is the convergency. How basically this convergence analysis based on the adamant decomposition method. How is convergence rate basically follow? So this is the W bar L basically is the series iterations, and via this method we actually calculate the convergency, and this is the maximum error via this main exact solution to the Tanigati series. So this is the maximum limit of the error. So within this the solution will be the better. Now, this is the first example. In this case, this middle operator d 5 by 2 basically is the capital fractional derivatives, and this is the initial conditions, and we obtain this method. We obtain this numerical and the exact solution via using the our adamant modify and two-step adamant decomposition method. We have discussed this. So basically, again, this is the operator form given in equation 34, and this is the linear condition. Basically, linear term involved in this L J, basically d 5 by 2 J, and non-linear term is the J square. So this is the non-linear condition given in question 33, and after applying this operator, because this is the main fractional operator, so we have chosen this operator for applying the inverse operator. So inverse operator of this fractional derivative, basically the inverse fractional integral. So we applying this fractional integral 5 by 2 with order 5 by 2 in the both side. In 34 we obtain 35, and with the help of this the J not this is the adamant decomposition process, where the J is the term of the series series solution, and Nji will be the approximate with the help of Adamant polynomial, and this is a value of the Adamant polynomial and Adamant polynomial in equation 38. So basically, now, after this recursion formula given in equation 39, we obtain J naught and J n. So J naught basically is the main our term. If you are using the domain, or if you are using the modify or a TSAT. So this is the main initial term. So with the help of this, we obtain the further iteration and obtain the values of the J 1, J2, and we see this after calculation. Why I'm writing this all calculation? Because of the we can see the values of this involved in the J2. So these all are unsettled term due to the value of J naught. This denote actually provided this unsettled term because this is not unsettled. If settled, then we obtain the closed form of the solution. So why this happened? Because of the chi naught and the Adamant polynomial. So if we are trying to reduce this unsettled term involving J naught, we can use the improved Adamant decomposition method, because in this method we improvise the Adamant polynomial and reduce the unsettled term, and then we are able to, if we reduce the unsettled term, then further iteration more more refined values provided more refined values, because we remove unsettled term, and this unsettled term basically one by one providing the large values of it, large values in the further iterations, and contributed the basically reduced the convergency rate, reduces the convergency rate with the via this unsettled term. So our main target to reduce the this unsettled term and obtain the closed form of this closed form solutions. So see eta 2, after iterating the first two, after considering the first two iteration, we obtain this solution, and then third. So this is the actually the picture. So if this we actually target series up to second iteration, this is the solution. If you are applying the limit, so of course this is not converges to the solution, because of the involving the unsettled term in each iterations. So via improved Adamant decomposition method, we are able to reduce this term, unnecessary term involved in the iterations, and we are able to find out the approximate solution with good convergency rate. Now our second method, modify, in which the this J naught actually is splitted. This J naught is splitted into the sigma 1 or sigma 2, namely. So basically the modify recursion formula, J naught is the first sigma 1, and the J 1 is the involving the second sigma 2, and the minus time of the first iteration terms involved in the recursion formula. And the further, this is the regression, and we obtain the exact solution via this. If we apply the modified Adamant decomposition method, so via this method we obtain exact solution just with one iteration, because in further this will we see if we integrate this, if we solve this integration, we obtain the 0. So basically further is also 0. So J naught is basically the exact solution of our considered problem. So similarly, we can going to solve the problem, consider problem, with the help of this TSADM. So again, we J naught is split into two component, and now one by one we are going to choose and try to verify the component. If this component satisfy the equation or condition, then it will be the exact solution. So sigma naught, basically y is equal to 0, satisfy if we check, then we are just putting the value of the J in place of J, y square, so it will be satisfy the equation and also the condition. Then J naught means y square is the exact solution of our considered problem. So basically in the two-step Adamant decomposition method, we obtain the exact solution in just one iteration, and modify provide the exact solution in just two iterations, and the domain actually is not capable to provide the solution, approximate solution, because of the involving the unsettled term in the each iterations, in each iteration of the series. So this is the main idea of the this three method. Now this is the example of variable fractional order, and here the eta theta, where the theta basically the, eta is the function depend on the theta, where we are derivative with respect to theta. So this is the basically variable order fractional differential equation. Again, this is the non-homogeneous, because our main target to find, try to implement these two step and comparison between the a domain modify and two step. So basically we have choose the, our focus main on the main our main focus on non-homogeneous fractional differential equations. So with the help of domain decomposition method, again we have obtained the exact solution, and with the in just one iteration. And this is the integral differential equation, and in which this is the complex order differential equation, where the nu is basically the complex number. And the TOCDM is also applicable for this type of integral differential equation. And again we obtain the exact solution. And now this is the comparison. If we solve the integral differential equation, the TSADM provide the exact solution in just one iteration, and modify provide the exact solution in two. And of course ADM is actually not capable to find out the solution because of the series nature. So series is not converging, so domain is not able to provide the solution. So we can also check the convergency analysis, and if you check this, so means the more distance between the two iteration is very large. If we check one by one, so this value is actually one by one become the larger because of the unsettled term actually pro distract the convergency of the iterations. Now see why we actually our target to why we use the TSADM, because we see this complicated problem in which we have extended the method into m dimensional, and this F capital F basically the source term. So this is the detail of the problem. So now we see that this is a source term is very complicated. If we use any other method, it's very difficult to tackle such kind of problem. And also if you're trying to implement the numerical method, so of course we have to restrict the dimension, but in the TSADM or modify TSADM is not actually required. So we can use this method for generalized problem also, and the particular solution is one by one putting the particular values, we obtain the particular solution for particular problem. So this method is very useful for generalized problem, if you are trying to get the generalized picture. So basically this method is also very useful, and we see that this is a very complicated term involved in the equations, but TSADM again is very useful for finding the solution. And this is a generalized analytical solution given equation. Of course this is the 52, and this is the generalized solution. By putting the particular value of n, m, and b, the problem is changed and solution will be obtained. So for uh, by using the numerical method, this is not possible, but by modify and TSADM is this very this method is capable to find out the general solution. So again, this is the general solution in which this is the research derivative used in the transport problem. So transport problem is also very important in our real problem. So this problem is again very complicated, and if you are applying the numerical method, so it's numerical is not capable to solve such kind of differential equation. So with the help of TSADM or modify, we again able to find out the exact solution. So see, this is the very complicated, and if you are using any kind of method, this is not able to there is no numerical method are able to find out the solution of the such kind of generalized problem. So this is the advantage of TSADM and modify both, but TSADM is the more superior than any other method because it provides the solution in just one iteration if it is applicable on the problem. So these are the other term involved in the source term. And now this is the stochastic in this case very important in this research field. Stochastic differential equation, stochastic fractional differential equation, stochastic differential are very useful because of the Brownian motion and Brownian motion in used in the random motion. So basically this type of differential equation very useful. And again in such kind of differential equation, our adopted method is again very well implemented and capable to find out the exact solution. And we know the stochastic means the means approximate equation. So we first this b row first remove from this because stochastic does not provide the exact solution. So the the exact solution of stochastic fractional differential equation does not exist. So in this case we second term removed, then we are capable to find the exact solution. In which here why removing this term, why we are going to remove, because this is the actually here we are removing the we are considering the motion is the uniform in the air or in the box, whatever you consider. So basically by removing this term, second term means capital lambda times of this integration. If you are removing this term, it means basically the b row is zero. B row means zero means motion are equal in the situation. So uh, by removing this term, we obtain the exact solution for such kind of differential equation where the star mark where the motion will be equilibrium. Now, yeah, these are the conclusion of the problem. 1 to 6 we have discussed, and all type of fractional order or variable order or complex order, the method are capable to solve for generalized problem, also for tempered result. And after generalize the problem, this method are very capable to solve and obtain the more accurate and more effective result by applying this method. So this method is very powerful in general, but of course this method is applicable on the non-homogeneous fractional differential equation. If J naught is zero, then of course modify NTSADM is not capable to say. There are so many methods also developed and improved, such as improved Adornment decomposition method is used for the constant coefficient, where the coefficient in term of the trigonometric. So basically improved Adornment decomposition very useful for such kind of differential equation. So one by one the Adornment, the modify, improved, and this all the method improvised method are useful for particular sections of problems. And we can check this, and we where the problem consider problem which one is more suitable we can see, because of the applicability of the method. And convergence rate is also very good, very committed, very complemented. So modify Adornment decomposition method and its upgraded version we can use. And in the only the few version actually frequently used, but there are so many modify version actually they have not used because of the complicacy of the method. If we a program, if we are capable to calculate, so this method is very capable to solve. And in the and also very good in comparative to other existing numerical methods. So this is the idea of further future plans. And now the our analysis term involved in the title. So now I'm going to establish the existency and uniqueness inequality for the considered problem. I have considered only one problem, and this is the actually consider or adopted theory or theorem for the establish the condition for the existency. So the Shepherd and the Crosnold key two particular fixed point theorem I have used. And this both are used on the compact set. And of course there are some uh, solution must be continuous and must be there are some restriction. So we can remove this restriction via some fixed point theorem. But our main focus in this talk is these two, Shepherd and Krasnolki. So now this is the Banach fixed point theorem. Via this theorem, we obtain a unique solution for the considered problem, and this is the basically contraction mapping in with the delta must be lie between 0 to 1. Strictly this delta is equal to 0, then this is the expansion, and in this case we have to check the contraction mapping. Of course, it's not contraction mapping, then we have to check the inequality, and we have to check in this case where the delta is equal to 0. So what is the condition? There may be many solution maybe exist in this case. So this is the idea. So for the this problem, for the previous problem, first problem I have discussed, in this case I have considered this case for establish the existing uniqueness condition. I have used for this problem. I am going to discuss the existing uniqueness condition. So basically, uh, so these are the assumption. But generalized problem, I have considered generalized problem, of course. So this is the assumption based on the capital H, and this is the Lexus condition must be satisfied by this function, and this is the second, the derivative term must be satisfied the Lexus condition, and after solving the contraction mapping, we obtain this value. After combining the contraction or the Banach fifth-point theorem, we obtain this inequality. If this inequality satisfies the considered problem, then problem is unique within this range. So this is the uniqueness, and this is the adjacent. This is the assumption for establish the adjacent conditions. So this is the result, and finally we have discussed in knowledge fractional differential equation application and three method: domain, TS, ADM, and modify and comparison between these three method and establish the conditions, existence uniqueness condition. I have also discussed in my research paper also, I have discussed the stability condition for the solution by using the Ulam higher stability. So these are the future plans in which you for researcher I have this idea, so that they can use the finite element method, Lie symmetricities. So this method, actually the second method, provide the exact solution for the differential equation. In the previously there is no actually article discussing such kind of differential equation because it's difficult to solve. If someone is capable, then this will be the very research idea is very good idea, because if we use this method and we are capable and we are able to solve the variable or complex order differential equation with the help of this Lie symmetry method, so it will provide the it will give the good research and good value of their work. So this is the idea. And second, the finite element method is also very good for the fractional differential equation. Here I am written arbitrary, it means we can use the variable, complex, and fractional differential equation. And I have particularly used Capito, Fabrizio, Artagana, and Hilfer. Hilfer provide the choice of functions, but also there are so many new and the classical fraction derivative exist. We can combine this derivative, and we obtain the mixed derivative equation, and we can solve by using the several this method. So we can obtain the values, so we can produce the new idea, and we can produce the new result in this case. And this is very helpful in the research field. So basically these are the future work, and we can actually work on this idea, and of course this provide the good value of research. So these are the some important references for using the, if you're trying to find a solution in other things. Okay. Thank you very much for your patience, and welcome to all this question. If
Thank you so
hello.
very much, ma'am. Dear participants, you can resolve your query by asking questions. Ma'am, hope there are no questions, ma'am.
Okay.
Let me continue.
If we have, if anyone want to discuss with me and anything else, PPT
Yes,
and
ma'am.
other stuff, papers, then I will happy to share with all. So I will share Dr. Kumar sir, and they will send to all participant. And
Okay.
if there any question, then you send the mail, and they will. Uh, okay.
Thank you so
Thank
much,
you.
ma'am. Thank you so much, ma'am. Every experience in your life is being orchestrated to teach you something you need to know to move forward. Yes, today we had an opportunity to hear your thoughts, and this will surely be going to encourage us in our future events. Ma'am, you are a real designer at heart. You have been consistent with the way you presented, and your presentations had the elegance and precision. Thank you for the session, ma'am.
Thank you very much for your invitation. I am very glad to you are inviting me for as a chief guest, and this is my first talk. I hope I am giving my best, and the
It was very fine, ma'am. Thank
all
you so
this
much,
my
ma'am.
stuff. Thank you so much. Thank you.
Thank you, ma'am. Feeling gratitude and not expressing it is like wrapping a present and not giving it. I request Dr. A. Maheshwari, Assistant Professor, to deliver the vote of thanks.
Thankfulness is the quickest path to joy. It is with great pleasure and gratitude to extend my heartfelt thanks to our esteemed chief guest, Dr. Pratibha Verma, Assistant Professor, Faculty of Engineering Technology, Shiksha O. Anushandan, Bhubaneswar, for accepting our invitation and sharing your knowledge with us. Your thoughts have truly inspired us. Thank you, ma'am. I express my sincere thanks to the management for this constant support and guidance for the smooth conduct of this program. I feel honored to mention my gratitude to our principal, Dr. N. Muthumani ma'am, for her perceptual support and constant encouragement to conduct this program successfully. Thank you, ma'am. I sincerely thank our head of the department, Mr. V. Ratanakumar, Department of Mathematics, for his unwavering support and encouragement. Thank you, sir. I express my sincere thanks to all the heads of the departments and staff members of PPG College of Arts and Science, their endless motivations. Thank you all. Moreover, I extend my gratitude to the organizing committee who have worked tirelessly behind the scenes to ensure the smooth conduct of this program. Thank you all. I would also like to express our sincere appreciation to all the participants for their active involvement and enthusiastic participation throughout the program. Your eagerness to learn has contributed immensely to the success of this event. Thank you, participants. Last but not least, I would like to thank each and every one of you who are present here today. Your presence had made this event truly special, and your support has been invaluable. Thank you all. Once again, I thank you for all. Have a great journey.
Thank you, ma'am. Dear participants, I request you to kindly fill the feedback form which is posted in the chat box. On Department of Mathematics behalf, I'm truly honored and humbled by the overwhelming support and encouragement from the guests and participants in and outside the box. Your unwavering belief on us has been a constant source of strength and motivation throughout this journey. All the best for your future endeavors. Hope we will meet in the succeeding programs. Thank you all for the perpetual support. Gentle reminder, we will be sending all your certificates as soon as possible. You all can leave the meeting once you fill up the feedback form. Thank you all. Have a great day.